Now this is chapter number 5 of our topic, Bismillahirrahmanirrahim. And a first order circuit with step response. Here we have a circuit with resistor and some sources, and a capacitor is connected to it, such that the voltage across the capacitor is called as Vt or Vc of t. Means C subscript means this is showing you the capacitor voltage. ICT is the capacitor current. Now first of all, we will convert this circuit to Thevenin equivalent, such that now our voltage will be called as V Thevenin, and of course that will be the function of time, and all the resistance will be presented by R Thevenin. And now these are the 2 points. The voltage across these 2 points will be called as V of t. This is the plus and minus. Now a capacitor is connected across it, so this is the value C. The current that is flowing through this loop will be called as IT. And if we write the subscript C, it means that this current is passing through the capacitor. Now this is the complete diagram. Now if we will write a loop equation for this diagram, so this will be equals to V Thevenin of t, meaning at any time, that will be equals to IT RT plus V of t. This is of course Vc of t. Now, as we already know that the current through the capacitor IC at any time, this will be equal to C dVc over dt, and this Vc is again a function of time. This is the capacitor voltage across the capacitor. Now we will rearrange our equation such that V Thevenin times t, not times t, V Thevenin of t, that is equals to R Thevenin times capacitance into dVt over dt plus V of t. So this is our source voltage. Let's say this is a step voltage, so we will write it as VA means source voltage times U of t means step voltage. So our equation will becomes R Thevenin times C dVt over dt plus Vt is equals to VA. As we know that this is for times t greater than equals to 0. So we don't need to write U of t at every time. So if we solve this equation, so we're left with Vt is equals to V natural response of t plus Vf, this is the forced response at any time. As we already calculated in our previous topics at Vn of t, we have calculated that was called as natural response. So in that case, if we calculated this one, so this was equals to R Thevenin times C into dVt over dt plus Vn of t. This was equals to 0 at time, of course, greater than 0. So its solution was Vn of t, that was equals to k e raised to power minus t over tau. And of course, tau is here R Thevenin times capacitance. And this whole scenario is for time greater than or equals to 0. Now we'll find out for forced response. So again, I'm writing here. So R Thevenin times C into dVf times t, forced response, divided by dt plus Vf t is equals to Va. Now here, one thing is to understand. This Vt, we have written this is equals to Va. Once this capacitor is fully charged, so this voltage Vt will becomes equals to Va. When no current will pass through it, now the V Thevenin will be equals to Va, and this Va will be equals to Vt. So that's why after forced response, we have written this whole equation to Va. Again, I have already told you, when your capacitor is fully charged, your Vf t, this will becomes equals to Va, and its derivative dVf of t divided by dt, that will be equals to 0, because there will be no change in the voltage at that time. And again, that for time t greater than and equals to 0. Now we will put both values into this equation Vt. So putting values here, we have V of t, that is equals to k e raised to power minus t over tau plus Va. Va is we have taken from this equation. Now furthermore, how we'll calculate? Let's do it. So at times t is equals to 0, V of 0, that is equals to k e raised to power 0 plus Va, that will be equals to k plus Va. And from our previous lecture, we have calculated this was equals to V0, the initial voltage of the capacitor. We want to see that if our capacitor was initially charged, and what was initially charged, and this was equals to V0, initial voltage of capacitor. Now furthermore, now we have evaluated k plus Va is equals to V0. So at times t, so our equation will becomes V of t, this is equals to V0 minus Va into e raised to power minus t over tau plus Va. So how would we do that? For times t is equals to 0, greater than or equals to 0. We have replaced the values at v is equals to 0, and this was equals to V0. And here we have already calculated that Vf is equals to Vt for times, and this one is equals to at times t that is approaching infinity, mean at steady state value. At that times, your df will be equals to Vf t divided by dt is equals to 0. So let's conclude our lecture. So at time t is equals to 0 plus, we have v0 plus, I mean just after switching, this is equals to v naught minus va e raised to power 0 plus va. So this way va will be cancelled out by va, so we are left with v naught, and v at infinity times, mean at steady state value, we have v naught minus va e raised to power minus infinity, and this whole factor will become equals to 0 plus va, that will be equals to va, mean your capacitor is fully charged, and this will be equals to your source voltage. And at just switching, your capacitor will be having only previously charged voltage. Okay, now let's redraw this graph. So this graph is very interesting. Now here we have time. This is 1 tau, this is 2 tau, this is 3 tau, 4 tau, and 5 tau. We only take up to 5 tau because after that, we consider that our capacitor has reached its steady state value. Now initially, if we have our V naught here, that the initial charge, and here we have VA, that is the steady state value or the forced response. So our capacitor will start from here and reach all the way to here. And again, it will not touch the axis line. The difference will be only less than 1%. So this was the forced response of RC circuits. Now, exactly in this lecture, we will discuss about the inductor. Now, we again start for the inductor diagram. Again, we have a box that is presenting some resistors and sources. Here we can see that a current that is coming out of it will be presented by IT, and of course we can write it as IL of t because this is entering in the inductor. Now the voltage across this inductor will be VLT, or just we write it as VL. Now this is the value of L. Now we will write in its Norton equivalent. Keep in mind, if we have RC circuit, we have to make Thevenin equivalent, and if we have inductive circuit, we will have Norton equivalent. So again, we have IN in Norton current. We have a resistor that is called as RN, and a current again that is IT, and we have an inductor L, such that voltage across this inductor will be VT. Again, we will write equations for this circuit. So we have L over R Norton into di t over dt plus I of t is equals to IA. Again, we don't need to write a step function here because we are writing for t greater than or equals to 0. For natural response, our IN will be equals to k e raised to power minus t over tau, and the tau here is equals to L over R in seconds. And again, for time greater than or equals to 0. Now for force response, our equation will becomes L over R n d if divided by dt, and of course this is again the function of time, plus I of f times t, this is equals to IA, means source current or the maximum current in which our inductor current will become equals to IA. Now for steady state condition, when a current is passing through this circuit and the current is not changing anymore, so the inductor current will becomes equals to IA. So at that times, your IT f, that will be equals to IA and differential of IF t divided by dt, and DI a over dt, that will be equals to 0. It presents that now no current is changing anymore. So setting all these values, we have IT that is equals to IN of t plus IF of t. So putting all the values, so we have k e raised to power minus t over tau plus IA, and this one is equals to I know. So we can calculate at times t is equals to 0. This factor will be e raised to power t over tau, that will becomes equals to 1. So we will be left with, at t is equals to 0, we are left with k is equals to I naught minus IA. Now again, we put all the values here. So I of t, this will be equals to I naught minus IA e raised to power minus t over tau plus IF, and for that case, this is equals to IA, and this is in amperes. If we plot the graph will be again same as for the capacitor circuit. So again, let's draw. So we have time axis here, and this is, let's say, 5 tau, and this is our I naught, and this is our IA. So at steady state value, the current will start from here and it's reach to the maximum value at this point. And again, it will not touch this axis line, it will be a slight difference, but the difference will be less than 1%. So we consider that our inductor has reached to its steady state value, and its value is IA. In proceeding lectures, we will perform some of the numericals and try to understand these equations in detail. Thank you very much.